Hello. Now we are going to look at normal curves and the empirical rule that helps us to understand their shape or distributions. So what is a normal curve? Well, a normal curve is something that comes out of drawing histograms of our data sets. So if we have a histogram of the heights of sixth year students, so we go out and we measure all of the heights of sixth year students, and we go to plot that information on a histogram. So our frequency would be on the y-axis and our heights of students would be on the x-axis. In this case, the heights are in centimeters. We would break up all of the heights that we measured up into separate buckets, into separate groups, and then we'd say how many people would have a height between these two measurements. So say in the middle bar here, between 170 centimeters and 180 centimeters is this group here, and there were 30 people, 30 students, 30 sixth-year students who had a height between 170 and 180 centimeters. And what we see with our histogram is that it has a kind of a hill type shape. Most people have heights that are close to the mean. The mean, if we got the mean of all of our heights of our sixth-year students, in this case, is 175 centimeters. So most people have a height that's fairly close to that average, to that mean. And there are a very small number of people who have heights that are much, much taller, and a very small number of people who have heights that are much, much shorter. So most people have a height that's fairly close to the average, and the further away from the mean or the average height that we get, the smaller the number of people we're going to come across who have these unusual heights. So because we keep seeing this shape in our histograms, not just when we get the heights of people, but if we get their weights, or if we get the weights of something that we are manufacturing, or the size of something that we are making in a factory, this hill shape keeps coming up, where most of the things we're measuring in a population have a size or a weight that's fairly close to the mean, and then there's very small numbers that would be a very big distance away from the mean. And because we keep seeing this hill shape over and over again when we are taking our measurements of data, we created a curve that was approximately the same shape as the hill we kept finding when we drew our histograms. And the reason we did that is because if we can draw a function, this is it's a fairly complicated function, but this is a function that we can write out exactly. And because we can write it as a function, we can do a lot of analysis with it. One of the problems with histograms is because they're just kind of blocks of data grouped together, we can't do very good, very advanced analysis or understanding of what the data set is telling us. By drawing a curve that's actually a function, it allows us to talk very accurately about the behavior of the overall group. If we assume that this curve is an accurate representation of the thing we're measuring here, it allows us to do much more advanced mathematical work with understanding the behavior of the group overall. And this curve that approximates our histograms that we keep drawing when we take our measurements is called the normal curve. Outside of our course, it's often actually called the bell curve because it looks a little bit like a big bell shape. So it's sometimes called the bell curve, but normally we are going to call it the normal curve. And I'll say it just comes from trying to draw a function that has the same shape as the histograms that we keep finding when we're measuring our populations. So if we take our normal curve version of this histogram, it has the same mean, and we have most people, our frequencies are going up here, so we have most people have a height that's fairly close to the mean, and then as we go further out, so this is getting taller, we have very few people who would be much taller than the mean, so we don't have very many people at all. The frequency is very low for people who would have a height of 190 centimeters. So that's what our normal curve is doing, and just in terms of our notation, we have x bar means the mean, and we have our pulled out 6 looking thing is our standard deviation. The if we like, kind of the average distance a data point is from the mean. It's not actually an average, but that's kind of a feel for what it means. It's a standardized distance all of our data set, all of our data points are from the mean. So that's our normal curve. And one of the nice things that having a standard curve does is it allows us to talk about the shape of that curve in general. So what we can do is say, when we have normalized data, when we have something that follows a normal distribution, which a lot of real world groups do, we can say that 68% of our population is within plus or minus 1 standard deviation of the mean. And 95%, so almost all of a population, is going to be within 2 standard deviations of the mean, and very much almost everybody, 99.7% of a population is going to be within 3 standard deviations of the mean. Now this is a little bit abstract at the moment, so we're going to put numbers to it now, but the usefulness, or one of the things that's very useful about our normal curve, is it allows us to describe the percentages of people in a group that are going to be a particular distance away from the mean. And this can be really useful for helping us to understand the behavior of populations. So if we take an example of a population, the people who are doing PE, a bunch of people in PE ran a race, and their times for running the race are normally distributed. So they would follow this pattern. So the mean time, when we got all of their race times and got the average of them, got the mean of them, the mean time was 54 seconds, and the standard deviation of our data set when we calculated it was 5 seconds. So 95% of the students took how long to finish the race? Well, 95% is from our empirical rule. That would be between 2 standard deviations away from the mean. So we are interested in how long 95% of the students took to finish the race. That would be within 2 standard deviations. So the answer would be, we want to know this range of values. So X is our outcome, our students' finish time, and 95% of the students are going to be within 2 standard deviations of the mean. So we can calculate this. We know the mean, we're told in the question, is 54 seconds. And we know the standard deviation is told to us is 5 seconds. So we know that 95% of our students are going to be between 2 standard deviations from the mean. So it's going to be between 54 minus 2 groups of 5 seconds and 54 plus 2 groups of 5 seconds. So that's going to be 54 minus 10 is going to be 44. And 54 plus 2 groups of 5 is 10, between 64. So 95% of our PE group ran the race in a time between 44 seconds and 64 seconds. So 95% of our PE group ran the race. They took between 44 seconds and 64 seconds to finish that race. So because we were able to use our normal curve, we were able to describe the behavior of that group in a way that we couldn't have if we just drew it as a histogram. So how can we use that same argument in this situation? The masses of carrots in a shop are normally distributed, or is normally distributed. Find the mean and the standard deviation. So again, the squashed or pulled out looking 6 is the standard deviation. Well, we've been given some information here. We know that 68% of our group for our masses of carrots is between 430 grams and 470 grams. So 68% means we are plus or minus 1 standard deviation away from the mean. So that means we can write down this relationship here. So we know that the mean minus the standard deviation would give us 430, and we know the mean plus 1 standard deviation would bring us up to 470. Now we may be able to see that that means that the standard deviation has to be 20, because we've gone up by 40 when we've done 2 standard deviations. But we can do this mathematically just by doing simultaneous equations. We have 2 things that we want to know about, the mean and the standard deviation, and we have 2 equations that we can write down for them. So we can just add those 2 things together, because we have minus sigma and plus sigma. And when we add them together, when we add those 2 equations together, like we would for any simultaneous equation, we will end up with 2 times our mean ends up being 900. So our mean weight, or our mean mass, I should say, of carrot in this particular shop is going to be 450 grams. And now we can find the standard deviation, because we know the mean plus our standard deviation would bring us up to 470. So 450 plus our standard deviation gives us 470. And we can rearrange that equation in order to find our standard deviation has to be 20 grams. So that's how we can use our normal curve. If we know 68% is between 2 particular values, well, we know 68% would be between minus 1 standard deviation and plus 1 standard deviation of our mean. So that allows us to write down this argument, and when we've done that, then we recognize we have simultaneous equations can help us to solve the problem. But our original argument comes from our empirical rule. Now, 99.7% of our carrots have masses between what? So we want to know 99.7%, or almost all of our carrots, will have masses between what value? Well, 99.7 is again part of our empirical rule. That's plus or minus 3 standard deviations. So we know we would be dealing with x bar minus 3 standard deviations and x bar plus 3 standard deviations would be covering 99.7% of our group. So we know the mean is 450 minus 3 groups of our standard deviation of 20. So our mass of our carrots, of 99.7% of our carrots, has to be between these 2 values, plus 3 standard deviations, has to be between these 2 values. That's 450 minus 60 would be 390 grams. And that would be 450 plus 60 would be 510 grams. So what does that mean? It means that 99.7% of our carrots in this shop are going to be between 390 grams and 510 grams. And that is how we can use our normal curves and the empirical rule to help us understand our groups better when we have our data sets. And that is what we need for now.